This is a video on finding the posterior distribution in an exponential model. A random variable has an exponential distribution with rates lambda if its probability density is the probability of x equal to lambda e raised negative lambda x. It looks very much like the exponential decay model that you might have seen in algebra. It sort of is closely related. Your lambda is the rate parameter, and it also mentioned that the probability x is less than or equal to some value x is simply given by 1 minus e raised negative lambda x. That's what we call the cumulative distribution function. So an example would make sense here before we move forward. Suppose the rate at which a battery decays, or in other words, its life expectancy, it's decreasing, or it is about 0.5 years. And let x be the battery life. And it has an exponential distribution with rate lambda equals 0.5. And let's say we want to find the probability that the lifetime of the battery is at most 1 month. Well, if it's going to have a lifetime of about 0.5 years in general, so we expect it to last for at least 6 months, and we are saying, well, what are the chances that the battery life would be at most 1 month? We're saying x is less than or equal to a month is 1 over 12, which is 1/12 of a year. So if I put it in the formula, I have 1 minus e raised negative 1 over 12 times 0.5. So we would end up having (0.04 0.08 as the answer. In other words, there is only a 4% chance. But oftentimes that is not the reasonable type of question to ask, because I should rather want to know, well, how long this battery is going to last me. Well, so the suitable question would be, well, what are the chances that the battery that I buy is going to last more than, say, 2 years? So we want to find the probability So from a practical standpoint, this is a better question to ask, because we want to know the probability, what are the chances if I bought a battery that it is going to last for more than 2 years. Now that would give us an idea into the longevity of the battery. So we can use the formula but we are trying to find the probability of x greater than or equal to 2. But in reality, the formula that we have is the probability x is less than or equal to some value x. So we have to do 1 minus the probability of x less than or equal to x, because the two terms are complements of each other. So what we have here would be 1 minus e raised minus 0.5 multiplied by 2. So if we simplify, we have 1 minus and minus 1 plus e raised minus 1. And that would give us 0.3678. So the probability that the battery would last for more than 2 years would simply be 36%. Now you may want to ask the question, well, what are the chances that it is going to last for more than 10 years, for instance? What are the chances it is going to last for more than 10 years? In that case, we simply replace that would simply be e raised negative 0.5 times 10. And you can see the probability is decreasing. So naturally, this would be a very, very small probability. Now, what if we had it at 100 years as the rate? So we would have negative 100 times 10. And that would be 0. because you may say, well, it doesn't make any sense, because if I said that the battery is going to last for 100 years, and here I have a simple question, what are the chances that it is going to last for more than 10 years? Why should this probability be 0? Now, this is where the tricky part comes into play. When we say the rate here of 0.5 years, the average or the expected value is 1 over lambda. And the variance of an exponential distribution is 1 over lambda squared. So if we plug in the value, we have 1 over 0.5, which is 2, and the variance of x would be 1 over 0.5 squared, and we will get 4. So if in reality I would want to have an average life expectancy of 0.5 years, the value of lambda must be 2. So $100 must equal 1 over lambda. This would imply lambda equals 1 over 100. So that would be the correct parameter to use if we want to look for 100 years average life expectancy. So if I change the question and said, well, what are the chances that I have a battery that has an average of 100 years life expectancy? So I would have 1 over 100 multiplied by 10, because I'm trying to find the probability that the battery would last for more than 10 years. And it's a 90% probability. So, so now that I pointed that out, in the question, the rate parameter is just 0.5. But in terms of the interpretation, the average expected lifetime, or the expected lifetime, should rather be one over lambda, which is 2 years. So we have 1 over lambda. So in terms of a problem, everything sort of looks peachy and nice, but we have to understand this key concept of how the rate parameter is related to a practical interpretation. So it is quite important, or else things could get easily confusing when we do posterior distributions. Okay. So, here is an example. Well, before we get to the example, let me do the likelihood function. So suppose x1, x2, all the way up to xn is an independent sample of exponential random variables, and let's say they have a rate parameter so of lambda, then the likelihood function so probability of lambda given the evidence, the data. So with our notation that we have used so far, theta is lambda and data is simply x1, x2, all the way up to xn. Will be proportional to the product of I equals 1 to n lambda e raised lambda multiplied by xi. So I'm going to, in this case, the proportionality constant is just 1, but I'm just going to keep it as is for now. So proportional to lambda raised n, I'm multiplying lambda to itself n times. And the bases are identical, so if I keep adding the powers, I would end up getting minus lambda sum I equals 1 to n xi. Now we know the sample mean is 1 over sum I equals 1 to n xi, which would imply the sum I equals 1 to n xi is equal to n times x bar. So I'm going to rewrite the likelihood as lambda given d, which is proportional to lambda raised n e raised negative n lambda x bar. So what should we do with this likelihood function? So here is an example. Suppose 12 batteries are randomly selected and their lifetimes are found to be 1.79, they're all in years, 2.18, 4.92, 5.49, 3.12, 7.19, 10.12, 3.36, 7, 2.19, 3, 4.2, 5.1, and 6.8. So these are the lifetimes of 12 randomly selected batteries, and they are in years. Now, we want to use an exponential model. So So we want to study the battery lives using an exponential model, and we want to know the reasonable value for lambda. Is it 0.8 or is it 0.6 based on the data, which is more likely? And this is where the likelihood function comes into play. So let's see. So we know the likelihood function is lambda raised n e raised negative n lambda x bar. So let's go ahead and find the mean. So here we have lambda raised 12 e raised negative 12 times lambda. And it ends up being 4.675. So we have lambda raised 12 e raised negative 12 multiplied by 4.675 times lambda. So our objective is to see, well, given the data, is lambda equal to 0.8? So we have the 12 observations. What are the chances that lambda would be 0.8? Well, let's plug in the value and see what we get. So 0.8 raised 12, e raised negative 12, 4.675 times 12. And that gives us an answer of 0. Let's do 0.6. Oh, I'm sorry, I made a mistake here. Thought that's weird. I was questioning myself because that 0 seemed quite weird to me. So 0.8 raised 12 times e raised negative 12 times 4.675 multiplied by lambda, which is 0.8. And that gives us 2.217 times 10 raised negative 21. In problems like this, it is very, very likely that we would encounter really, really small values, which is why people like to put this in logarithmic scale and call it the log likelihood. But I'm just going to keep it as is here. So 0.6 raised 12 times e I'm plugging in 0.6 for lambda. And we end up getting 5.241 times 10 raised negative 18. So we want to go for the maximum likelihood. So of the two, max likelihood is when lambda equals 0.6. So given the two choices, which one should we go with? Or which is reasonable? Now, could I have guessed, I knew the answer is 0.6, or it is going to be 0.6 at the very beginning. Well, how did I do that? Well, if you recall, the expected value is 1 over lambda, and expected value is the theoretical average. So 1 over lambda would be equal to the mean that we have, the sample mean, if I put 4.675, which would mean an approximate value for lambda is 1 over 4.675. And the most appropriate lambda value for this problem would rather be 0.2139. So that's just based on likelihood. In other words, we did not have any prior information here. So now we're going to bring in the prior information. So we go for a posterior distribution. In other words, what are the chances that we get I have to go back here, got way too excited and messed up the notation, so I apologize. So this should be so the likelihood is given a parameter. What are the chances of seeing the data? I messed up on the notation here. They're not the same. We should know this. I apologize. Okay, it was just a notational mistake. So the posterior distribution for lambda is probability of lambda given d, and that would be proportional to the likelihood data given lambda multiplied by the prior. So we know the likelihood in our case is lambda raised n times e raised negative n lambda x bar. Now, we want to have a distribution that looks like the likelihood, and we readily have a nice little distribution, which is the gamma distribution. So the conjugate prior for lambda here is gamma alpha beta distribution. So we would simply have lambda raised alpha minus 1 multiplied by e raised negative too many signs here, so lambda times beta. So that would be the prior for the exponential model, and it is a conjugate prior. So prior for lambda, and the parameters are alpha and beta. So I'll put a note, the expected value for a gamma distribution is alpha over beta, and variance is alpha over beta squared. So we have the probability of lambda given the data. It's proportional to lambda raised n, e raised negative n lambda x bar, lambda raised alpha minus 1, e raised negative lambda times beta. So the bases are identical for the lambda part, so I'm going to combine the powers, n plus alpha minus 1, and I'm going to combine the exponentials. I'll have negative n lambda x bar, negative lambda times beta. And I have lambda in common. So I would end up getting lambda times n x bar minus beta. So if we observe closely, we can see that that looks very much similar to a gamma distribution. So the original gamma distribution was right here. And you can see lambda is the variable, the power was alpha minus 1, and we had e raised minus lambda beta. And if we take a look at the current expression, alpha is getting replaced by n plus alpha, and beta is getting replaced by n times x bar minus beta. So the probability of lambda given the data in this case is proportional to a gamma distribution with n plus alpha and n x bar minus beta as the parameters. So the posterior mean so for a gamma, the mean is alpha over beta. So for the new parameters that we have in the posterior distribution, we have n plus alpha over n x bar minus beta. And the variance would be alpha over beta squared So that is our final answer. Now, let's say if we can find the posterior distribution for the example that we had, which is right over here with the 12 batteries, and of the two reasonable values that we had, 0.8 and 0.6, it turns out 0.8 is a much more reasonable value, and in reality the actual estimate is 0.2139. That is what we call the likelihood estimate. Now, based on everything that we see here, the average lifetime in that case is about 1 over 0.2139. It's about 4.675 years. And that is what we have based on the sample over there, without any prior information. Now, the same example, so what is the posterior distribution if the, I've made a notational error here, or algebraic error, it's plus, and plus. So what is the posterior distribution if the prior is gamma 2, 0.6? So we know the posterior distribution probability of lambda given the data is gamma, and the parameters are mu post and n plus alpha and nx bar plus beta. So we know n is 12, alpha from the prior is 2, x bar from our problem is 4.675, and beta is 0.6. So I'm going to plug all the values in, and that would give me the posterior as gamma 14, 12 times 4.675 plus 0.6. So that simply ends up being 14, 56.7. So how do we find the mu post, the posterior mean? Which is simply n plus alpha over n times x bar plus beta, so it's 14 over 56.7. we have 0.2469, and the variance is the same, which is n plus alpha divided by 56.7 squared. We have 0.0044. If the variance is 0.0044, it would imply that the standard deviation is the square root of that. And we get 0.066. So we have the posterior distribution. Now let us go back to the original problem where we simply had the likelihood estimator. So we have the posterior mean and posterior standard deviation. And I'm going to extend the example by asking this question. Suppose lambda hat is 0.2139 for the sample, or using the sample. And here we have mu post and sigma squared post. So what we want to do is we want to find the probability that the battery is going to last for more than 4 years using lambda hat equals 0.2139. And we want to find a 95% HDI for lambda using the posterior and normal approximation. And lastly, we're going to answer another important question: find the probability of x greater than 4. In other words, what are the chances that it is going to last for more than 4 years? Well, let me rephrase that question. I'm going to hold on to the question and ask the question later on. So what I'm stating here is, let's just forget about the posterior that we just derived, and we go back and look at the sample. We end up using the expectation of the sample, and in reality, it happens so that the value of lambda has to be 0.2139. That would correspond to an average lifetime of 4.675. Now, I'm going to use that value, whatever the sample gave me, and I'm going to arbitrarily ask the question, what is the probability that x would be greater than 4? And I know that x is exponential with lambda equals 0.2139. I put a hat to indicate an estimator. So we know the probability of x greater than 4 is 1 minus e raised negative lambda times 4. So I have 1 minus 1 plus e raised negative 0.2139 times 4. And those two would go away, and the answer would simply be 0.4250. Great. Now we want to find a 95% high density interval for lambda using normal approximation. So we know the posterior mean is 0.2469, and the standard deviation is 0.066. So the margin of error would be 0.2469, which is mu post. .066, which is the standard deviation of the posterior, multiplied by the critical value 1.96. We get 0.1294. So the interval lambda can be anywhere from 0.2469 minus 0.1294 and 0.2469 plus 0.1294. Here is the big question that I wanted to ask earlier. So, we know we used the prior information and we came up with an interval instead of a single value. We're saying, well, there is a 95% chance now that we've brought in some subjective information. The value of lambda would be from 0.1175 all the way up to 0.3763. If that is the case, so now that we have the prior information and the posterior distribution, is lambda equals 0.6 reasonable? Well, obviously, no. Is lambda equals 0.2139 reasonable? The answer would be yes, because 0.2139 is between 0.1175 and 0.3763. So naturally, what would happen is that if you keep on increasing the sample size, eventually the estimator that we have here will be very much similar to what we would have with regular exponential distribution and maximum likelihood, which is 1 over lambda. So I've brought in some prior information and things changed, and yet the original likelihood-based estimator, the expected value of 0.2139, still falls in the high-density interval that we just found, which is lambda is likely to be between 0.1175 and 0.3763. And how credible is that interval? We are about 95% sure that lambda would lie between those two values.